Hello, Algebra 1. We are in lesson 24 today, applications of systems of equations and inequalities. Equations, we have an equal sign. Inequalities, we have many options. Greater than, equal to, less than, equal to. When we talk about systems, we mean more than one equation. Goodness, sorry, my iPad just lost it. More than one equation with more than one variable. Excuse me. So if we were in class, I would have you guys brainstorm this one with your neighbor. But we're not in class. You guys are somewhere watching this and taking notes, and I am sitting in my office at home hoping the kids don't interrupt me. So let's just talk about it. We talked about this as systems of equations, so we're going to have more than one variable and probably more than one equation. This says, in Lewis Carroll's Through the Looking Glass, Tweedledum says, the sum of your weight and twice mine is 361 pounds. So you got Tweedledum says this, I'm underlining it in red. So he says the sum of your weight, we're going to say your is y for Tweedledum. We're also going to say the word sum means plus. So I have the sum of your weight and twice mine is 361 pounds. So in Tweedledum's case, x is going to be mine. And is, when we see the word is, we mean equals. Cool? Now, I have Tweedledee replies, the sum of your weight and twice mine is 362 pounds. So once again, I have sum, which means plus, and the word is means equals. So in this case, your, Tweedledee is referring to Tweedledum. So x is going to be your, because Tweedledee is talking. And so the sum of your weight and twice mine. So when Tweedledee is talking, we have to say that y is mine. Mine would be Tweedledee. And your, well, sorry, and this mine is Tweedledum. And that your is Tweedledee. And the blue your is Tweedledum. So let's write some equations. So when Tweedledum is talking, he says the sum of your weight, sum, and twice mine is 361 pounds. And then Tweedledee talks and he says the sum of your weight plus twice mine is 362 pounds. Well, do I have enough information to solve the equation? Generally, if you have two unknowns or two variables, I have two variables here, y and x and y, you need two equations to solve your system. A system, if I have two variables that we don't know what they are, I need two equations so that I can solve it. So let's go ahead and see if we can solve these. I'm going to put both in x first and then y. Sum is 361 and the sum is 362. I'm going to multiply this second one by a -2 because I like to add and not subtract. And I'm going to get 2x plus y equals 361 and -2x minus 4y equals 724. Okay, I'm going to transfer this to another slide so I don't have to squeeze everything in. So hold on a second. So I transferred this over and started to solve for y. Realized I wasn't recording, so I started recording and I'll catch you guys up. This is where we ended off in the last slide. I multiplied the second equation by -2, which gave me this equation right here. Then I added. Those cancel out. I have -3y and -363. Divide by -3, cancels those out. Divide by -3, and I get y equals 121. Now I can go ahead and plug this into any one of these equations up here. I'm going to say 2x plus 121 is 361. Subtract 121 from both sides because you're trying to isolate the variable. And I get 0, 4, 2, 240, divide by 2, and I get x equals 120. So what did we say on the last slide? Hold on, I'm going to go look. You have it written down though. On the last slide we said x was Tweedledum and y was Tweedledee. Cool, we did it. System of equations solved. All right, let's look through another example. As a reminder, what we did with this first example is we decided somebody was going to be the variable x and somebody else was going to be the variable y. We found some key words in the problem like some and is. We set up two equations to try to come up with some solutions, and that's really how we do this every time. These things aren't easy, but we can do it. Okay, we got it. There's always some patterns that we can figure out. So for this one, I have Lulu tells her little brother Jack that she is holding 20 coins. I've got 20 coins, all of which are either dimes or quarters. They have a value of $4.10. She says she will give him the coins if he can tell her how many of each she is holding. Solve this problem for Jack. So I know the total number of coins I have is 20. I've got so many dimes and so many quarters. So if I just count the coins, dimes plus quarters, is it dimes and quarters? Yep, dimes and quarters. I have 20 of them. That's just counting. So one equation is always going to be the counting equation. The other equation, it's going to talk about the values of those dimes and quarters. So I know a dime is worth 10 cents. And I know a quarter is worth 25 cents. And I know all of them together are worth $4.10. So here's the system of equations I have. Two equations, two unknowns. I am ready to solve. Just like the systems of equations we did last week or yesterday, last lesson I guess I should say, we need to get the variable either the d's to have the same coefficient in front of them or the q's to have the same coefficient in front of them. So I need to multiply an equation by 0.10. So if I distribute that 0.10 through, I will get one of the variables to cancel out if I subtract them, which I've told you guys I don't like subtracting, but that's okay, we'll do it. So 0.10d plus 0.10q equals 2. Because 0.1 times 20 is 2. And I'm just going to subtract from that 0.10d plus 0.25q equals 4.1. So I'm subtracting this whole second equation from the first. That means my d's term cancel. And I've got 0.1 minus 0.25. That gives me a negative 0.15. And a 2 minus a 4.1, that would give me a negative 2.1. Divide both sides. And I get Q equals 14. So I believe I have 14 quarters. If I plug it back into this equation, I will get 14, nope. I will get a certain number of dimes plus 14 quarters equals 20. Subtract 14 from both sides. I have dimes equals 6. So I have 6 dimes and 14 quarters. I'm going to check my math. 14 times 0.25 plus 6 times 0.1 gives me 4.1, $4.10. Yay. Cool. All right, exploratory challenge. I'm going to take it a little deeper. At a state fair, there is a game where you throw a ball at a pyramid of cans. If you knock over all the cans, you win a prize. The cost is 3 throws for $1, but if you have an armband, you get 6 throws for $1. The armband cost is $10. Phew. Write 2 cost equations for the game in terms of the number of throws purchased. One without an armband and one with. So let's look at the one without an armband. I'm going to read it again. 3 throws for $1. So the cost is going to be 1/3. So 3 throws for $1 times X. X equals the number of throws. So the number of throws, 1/3 times X, the cost. So if we have 3 throws, we would have 1/3 times 3, which is $1, right? So my first equation makes sense. 1/3 times X. Cool. Okay, that's without the armband. Now with the armband, I get 6 throws, but it cost me $10. Okay? X being the number of throws. This would be 6 throws, which if I did the math, I'd have 1/6 times 6. Let's write that a little different. I'd have 1/6 times 6, which is $1. So for 6 throws, it cost me $1, but I had to pay $10 to purchase the armband. So now I have 2 equations and 2 unknowns. Okay, that's 2 cost equations for the game in terms of the number of throws purchased, one without an armband and one with. Check. Next one says, graph the 2 cost equations on the same graph. Be sure to label the axis and show an appropriate scale. So my graphs were C equals 1/3 X and C equals 1/6 X plus 10. So I have a slope and a y-intercept. These are linear equations. So let's go ahead and try to graph them. You guys are getting serenaded by one of my children practicing piano. Hope you enjoy that. This first equation doesn't have a y-intercept, so I start at 0. And my slope is 1/3. So 1, 1, 2, 3. That's not a very good one. 1, 1, 2, 3. 1, 1, 2, 3. 1, 1, 2, 3. So I've got my line. Notice I'm only in the first quadrant. Okay, that's not a mistake. Oh, hold on. 1, 1, 2, 3. When we're doing real life graphs, the first quadrant makes sense because all of this is positive and all of this is positive. Because I can't spend negative money and I can't have negative throws, right? All right, now we have the cost of an armband. I have a y-intercept of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my slope is 1/6. 1, 1, 2, 3, 4, 5, 6. 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 1. Cool. So we're going to go like this. Oops, I don't want to do that. Cool. All right, does it make sense to buy the armband? I'm gonna push pause for a second and I'm gonna show you something real quick, okay? Give me a sec. All right, excuse me. Here we go. This looks better. I just went into Desmos and graphed one really quick. Now we can actually see where they cross. But I didn't label my graph, did I? Well, that's bad. Because the instructions say be sure to label the axes and show the appropriate scale. So here I have cost, which is my y-axis, and number of throws, which is my x-axis. My scale is spot on what you see. It's labeled. So now we can see that where they intersect is where it doesn't matter if you buy an armband or not. So at 60 throws, you can buy an armband or not, and your cost is the same. Well, when you go more than 60 throws, then you should not buy the armband. So more than 60, more than 60 throws, buy the armband. And I'll show you again why. This right here is no armband. So here we are, here we are, here we are. This is cheaper because on my cost axis it's less. This is below the armband graph, it's lower, so the cost is less. And then once we hit 60 throws, the red graph goes above the blue graph, so the cost becomes more for no armband. Okay, if we follow this one, the cost is too much, more, because it's higher on the graph, it's above the red graph, the red line. So this one is more expensive, more expensive, more expensive. Here they're equal, and then it's cheaper. So here we have cheaper, after 60 throws. They are the same at 60. Cool? Cool. All right, a clothing manufacturer has 1,000 yards of cotton to make shirts and pajamas. A shirt requires 1 yard of fabric, and a pair of pajamas requires 2 yards of fabric. It takes 2 hours to make a shirt and 3 hours to make the pajamas. And there are 1,600 hours available to make the clothing. Whew. What are the variables? Well, we have really the number of shirts and the number of pajamas. And we can say pajamas, yes. One of them is going to be X and one of them is going to be Y. Okay, it doesn't really matter, but one has to be X and one has to be Y. What are the constraints? What is limiting it? What are the barriers that you can't get by? And the barriers are how much time the manufacturer has and how much material is available. So our constraints, what are our limiting factors, are the amount of time and the amount of fabric. Those are the two constraints we have. Now we have inequalities for the constraints. Okay, this one's a little special. We have inequalities. Well, first of all, your shirts, the number of shirts you produce, has to be greater than or equal to 0. The number of pajamas you produce has to be greater than or equal to 0 because we can't produce negative things. And then let's go back and read the equation. I know that a shirt requires 1 yard of fabric and a pair of pajamas requires 2 yards of fabric, and that has to be, the amount of fabric you use has to be less than or equal to the total amount of fabric you have. Okay, that's the material constraint, the fabric constraint. Now we can look at the time constraint. Well, it takes 2 hours to make a shirt and 3 hours to make pajamas. And the amount of time we have to make those things has to be less than or equal to 1,600 hours. All right, makes sense? So please write those down. I'm going to graph this and put it on the next slide. So if you look here, I've graphed all the equations. What we're doing is putting constraints on our graph. So x has to be greater than 0, which is red, which you can't see because, gosh, right here, x is 0, up and down this line everywhere, and we shaded red in this direction. All of this got shaded red. But then we have y is greater than 0. This right here is the line y equals 0, and we shaded blue up. So that's why we have purple, right? We shaded red in this direction from that line, red in this direction. We shaded blue straight up. We got purple. So that's the only place our solution can be, is in quadrant 1. Then in green, I shaded the first equation, which I always tell you guys to put them in slope-intercept form. So x plus 2y less than or equal to 1,000. Subtract x from both sides. I have 2y is less than or equal to negative x plus 1,000. Divide everything by 2. Y less than or equal to negative 1/2 x plus 500. So this green one, if you look, it started at the y-intercept of 500 and went down a slope of 1/2. So down this would be 100 over 200, down 100 over 200, etc. And then this equation, if I put that in slope-intercept form, I would have 3y less than or equal to negative 2x plus 1,600, divide everything by 3, y less than or equal to negative 2/3 x, plus 3 goes into 1,600 not evenly, 533 1/3, which you see right here. It's my y-intercept. And my slope is negative 2/3, which is a bit steeper. So right here is where they cross, right? So what you see here, if you guys could sketch this on your homework, I need to go to the next page to show everything. Well, let's do this. We didn't label. So this right here, our y-axis is, let's see, y was the number of pajamas. So this would be pajamas. Our x-axis was shirts. And it's number of shirts and number of pajamas. So right here at this point, which is over 200, up 400, that is where everything is equal. All right? That is where I can make 200 shirts and 400 pajamas and use all of the fabric and all of the time. All right? If we are up in this range, I'm making more, let's see, that's the yellow line. I have time. This was my time constraint. Okay, if I'm right here where the green is, that is my fabric constraint, right? The various combinations of shirts and pajamas, it's possible to make for this manufacturer. These are all the various combinations. The only place that you can make, oh, that's way too big. Hold on. Let's make that a little smaller. Where everything is doubly shaded. This range right here. Where everything is doubly shaded, every ordered pair in this shaded area is where you can find combinations of shirts and pajamas that it's possible for the manufacturer to make. Okay? If we leave this shaded area, we are either running out of fabric or running out of time. But everything within this shaded area, where everything is true, everything is positive, is part of your solution. So this right here is called our solution. Okay, it's where everything is true to your statements. Cool? So let's do this. Suppose the manufacturer, this is part of your questions, suppose the manufacturer makes a profit of $10 on shirts and $18 on pajamas. How would it decide how many of each to make? Well, basically the manufacturer wants to make as many as possible, so the maximum should be at one of the endpoints of the shaded region. So we're trying to make as much as possible, so we'd want to go for one of the endpoints at the shaded region. So that would be the maximum number of shirts and pajamas, and that's going to be your most profit, where profit is going to be $10 per shirt and $18 per pajamas, right? Next slide. If we have $10 per shirt and $18 per pajamas is our profit. Oops. If we go to those endpoints, we would read one of the endpoints was 0,500, and that would give us no shirts plus 18 pajamas equals, do that math, I get $9,000 profit. Another endpoint was 200, 400. Then I would have 10 times 200 plus 18 times 400, and I would get a profit of $9,200. And then that other endpoint was 800, so 10 times 800 plus 18 times 0 gives me a profit of $8,000. So which one should he pick? Which one gets you the most profit? Well, duh, 9,200 is more than 8,000, more than 9,000. That is the most profit that I can get, which is very, very cool. Which means we answered all these questions. I just didn't do it here. And I don't know what this slide is for. So good work today. This homework, this problem set can be a little bit challenging because there is no one exact way to do everything right. Cool? Eyebrows. There we go. That's a smile. It looks like a chin. All right. Take care.